Okay, so let's continue our discussion of constructible numbers. We saw in the last video that the sum, difference, product and quotient of two constructible numbers are again constructible numbers. So that of course gives rise to this fact: the set W of all constructible numbers is a subfield of the field of real numbers. Okay, so all those things that this set is closed under the formation of sum, difference, product and quotient, that can be summarized like this by declaring that the set, we are calling the set of constructible numbers W. This set then becomes a subfield of the field of real numbers. As a consequence, it contains the field of rational numbers as its own subfield, where this is the field of rational numbers. That is, W is an extension of the field of rational numbers, and the field of real numbers is an extension of W. In other words, the situation is like this. Okay, so this is just a simple consequence of what we have already seen. Now, before moving on, the author simplifies this phrase construction by straightedge and compass to simply construction. So, for example, if we have to say constructible number or say constructible something by straightedge and compass, that part by straightedge and compass will be suppressed. When we use these words construct, constructible, construction, that will always mean by straightedge and compass. And also the way we have defined in the previous video what we mean by constructible objects. So by straightedge and compass, that is understood. It will not be said explicitly. Right. So now what we are going to do, now we are going to use this fact to see if we can recognize which real numbers are constructible and which are not. So we are going to go towards a kind of criterion for that. But we won't be doing that. I mean, whatever now we need to do, we won't do that just for the field of constructible numbers, but in general for any field F that lies between Q and R like this. So the next paragraph, it goes like this. Let before this there is another line, just one line, which it just simply follows directly from the definition of constructible number itself. What it says is that if W is an element in W, that is, if W is a constructible number, then we can get to W by applying a finite sequence of constructions. But that's how we have defined the notion of constructible numbers. You can go to the definition and you can see that that is the case. So actually, what does it mean for W to be constructible? If you just for once, if you think about the actual definition of constructibility of a number, then it just simply is this. If you can find 2 points in the plane which are constructible and such that the distance between them is the absolute value of W, then by definition W is called constructible. But to get to these constructible points, you have to start from those initial 2 points which are given to you in the beginning itself, which are at a distance 1 from each other in the plane. And then we apply the 3 allowed construction by straightedge and compass to get more constructible figures. And that way, we eventually, after a finite number of such compass and straightedge constructions, we get to 2 constructible points such that the distance between them is this. Then we call W constructible. So that means in order to get W, we have to pass through a sequence of such construction steps. That's what this single line is saying. So now what we do, now in this next paragraph, I was going to write it there. We are going to consider a general subfield F of the field of real numbers, which of course would contain the field of rational numbers, like this. Let F be a subfield of R. Note that just simply this itself implies that Q is a subfield of F, because we already know, we have seen before, that any subfield of the field of real numbers contains the entire subfield of the rational numbers inside of it. So we need not mention that separately. That is automatically true. Now, consider all points x comma y in the Euclidean plane. Both of whose coordinates x and y belong to this subfield F. Euclidean plane means, as I said, it's just R2, right? So in R2 we are considering those points, both of whose coordinates are elements in the subfield F. Then we call we call this set of points the plane of f. And within brackets I write clearly this set is this Cartesian product. And there are two extreme cases. If our field f is equal to the field of real numbers itself, because that is also a subfield of R, then this set of points is just the entire Euclidean plane, the entire plane. And if our f is the field of rational numbers, then this plane of f in that case is just the collection of those points in the Euclidean plane, both of whose coordinates are rational numbers. But in general, this is the plane of f. This is called the plane of f. Now, here are some facts about this object. Any straight line joining two points in the plane of f has the form ax plus by plus c equal to 0 with a, b and c in f. Okay, this is a fact. That is, if you take 2 points in the plane of f, that means for both of those points, both the coordinates are elements in f, then you can think of an ordinary straight line in the actual Euclidean plane joining those 2 points. Then that straight line will have an equation of this form. Any straight line straight line has the form means straight line equation is of this form, that is understood of course, where these coefficients a and b and this constant term c are all elements of f, and this is one exercise which now we are going to solve. This is exercise 2 in the text. Just for the sake of writing the exercise, the statement, let's just write it once more. Prove that it may not be immediately clear why we are doing these things, but once we finish all these considerations and prove all the necessary things, then we will see how that gets us towards what we want. That is a criterion for deciding which real numbers are constructible numbers. So here we have to prove that a line in f has an equation where the terminology line in f of course means this. Actually the discussion goes on. We have stopped here to prove, to solve this exercise, but the discussion goes on, and towards the end of this paragraph such lines and circles are also going to be talked about. They are called lines and circles in F. Now, if you think of it ordinarily in a line in the field F, it does not make any sense. But this is just a way of expressing this fact that a line in F just means an ordinary straight line in the plane joining two points in the plane of F. That means F Cartesian product F. Okay, so let us now solve this. So we have to consider two such points. Let u comma v and s comma t be two distinct points in the plane of F, or in other words, they are two distinct elements in this Cartesian product, which just simply means that u, v, s, t, these are elements in the subfield S of R. Okay. Now note that they are distinct. Okay, they are not the same point. That is, we don't have u equal to s and also v equal to t. We do not have that. But it can of course happen that u is equal to s and say v and t are different. If that happens, then just you think geometrically, what will the situation be? Say your u comma v is here. Then if your s is equal to u, then the x coordinates of these 2 points are going to be the same. That means these 2 points will lie on a vertical line. But because they are given to be distinct, v and t are going to be, they have to be different. Now here we have drawn this, the points in such a way that v is greater than t. The opposite thing can also happen, you understand. So the straight line you see is, it will be like this. And the equation of this line will be what? Equation will just simply be this. X equal to u or x equal to s, anything you can write, because u and s are equal. That is because this is the condition that characterizes all points on this line. Any point on this line has x coordinate fixed, and that is equal to u. But the y coordinates, of course, they vary. So now we consider this special case first of all. If u is equal to s, then okay. Now, before I write these things down, let me give the line some name. That way it will be easy to refer to it. Let L be the line in the Euclidean plane. I should not write joining these 2 points, because that would be a line segment only, passing through these 2 points. And now we consider that special case. If u is equal to s, then the equation of L is x equal to u, because a vertical line Now, if you look at this equation and compare it with the form that is given, you see that in this case A is 1, what is B? B is 0, and what is C? C is minus U. So the equation, of course, it has this form because this is the general first degree equation in two variables. But the point here is that these numbers, these real numbers, do they belong to F? Yes, 1 and 0 of course belong to F because F is a field. Minus U belongs to F because U belongs to F, and again because F is a field, so F contains the additive inverse of every element. So if U is there, then minus U is also there. So that's why in this special case the claim is true. We are, however, not going to write things in this elaborate form. We will finally conclude. Now let's consider the other case. Say V is equal to T. If V is equal to T, okay, in that case what will happen? V is equal to T, then the points lie on a horizontal line where the y coordinates of all the points are fixed, and that fixed value is V. The x coordinate changes and changes the position of the point on this line. So what will the equation of this line be? The equation of this line is just y is equal to V, because that is the condition that characterizes all the points in this on this line. So then the equation of L in this case is y equal to V. Now if you think of this one also just like that one, in this case A is 0, B is 1, and C is minus V, and they also are elements in F. So now we can assume that U is different from S and also V is different from T. So that case is there now, left to us. U is different from S and V is different from T. Then the equation of L will be what? See, you recall what you learned in coordinate geometry or analytic geometry, where you have to write the equation of a straight line passing through 2 points. Right, you can use the point slope form. In fact, there is a form for writing that equation if 2 points are given, but ultimately it's the point slope form. So what is the slope of the line L which joins these 2 points or which passes through these 2 points? Difference in their y coordinate, that is V minus T, divided by the difference in their x coordinates, that is U minus S. Where you have to keep in mind that if you are writing the difference in the y coordinate in this order, that is V minus T, then you have to maintain that same order in the denominator also, U minus S. If you write T minus V, then you have to take S minus U, because you see that you can multiply and divide the numerator and denominator by -1. The quotient will be the same, but you will get that thing. Actually, they are the same thing. So this is the slope of the line. And now you can use the point slope form to write the equation of L, for which you can either use this point or that point. Ultimately, we are going to get the same equation. So if we use this point, then the equation will look like this: y minus y coordinate equal to the slope times x minus x coordinate. We are really not using this condition here, but we are of course using the condition u not equal to s here, because that's why we can have u minus s in the denominator without the fear of it being 0. That is not possible now. It won't be 0. So let's just write it. This is y minus v equal to times x minus u. Now we are going to manipulate it a little bit to bring it to that form. So first we multiply on both sides by u minus s. I am writing this if and only if just to show that these are all equivalent. The equations that we will write here, they are all equivalent to one another. So just like you can go from here to here, you can also go back. Okay. So if we multiply things, not all, multiplying all the things out, but keeping this with y. So we do not need to multiply u with y and also minus s with y. We just keep this, and with this of course we multiply. We do the multiplication. Minus uv minus minus plus sv, that is equal to v minus t times x minus uv minus minus plus tu, and this will be equivalent to you can see that this minus uv and minus uv from both sides, they cancel out. And if we take all the terms on one side so that we can have that form, that required form, keeping of course this just like this and bringing all the terms over here on this side, then we get v minus t times x plus s minus u times y. Plus tu minus sv. So this of course is in the form ax plus by plus c equal to 0. And clearly v minus t, then s minus u, and tu minus sv are all elements of f. But why? That is because U, V, S, T, these are elements of the subfield F. So these elements, these real numbers are also going to be in F, and that comes from the fact that F is closed under the formation of sum, difference, product, quotient, all those things. And that's where the subfield nature of F comes into play. So finally we write, so in any case L has an equation of the form this, where A, B and C are elements in F. So that completes the solution and it proves the claim. Now next we are going to talk about circles in F. So this is how the author goes. Moreover, that means we continue our discussion. Having talked about lines in F, now we talk about circles in F. Moreover, any circle having as radius an element of F and having as center a point in the plane of F. That means having as center a point which is an element coming from the Cartesian product F cross F Cartesian product F. For any such circle, it has an equation which is of this form. Has an equation of the form x square plus y square plus is he okay, A, B and C again. Where again these elements are, these real numbers are elements in F. And you of course understand if by any circle we mean a circle in the Euclidean plane R2. Now this is also one exercise and we are going to solve it now. So as we progress through the section, we solve the whatever issues arise, we solve it then and there itself. So this is the exercise 3. Prove that a circle in F. Now just like a line in F, by a circle in F we mean a circle of this type, whose center is a point in the Cartesian product F cross F and whose radius is an element in F. So so that's what a circle in F means. A circle in F has an equation as an equation of the form x square plus y square plus ax plus by plus c equal to 0, where a, b and c are field elements. Okay, so now we are going to prove this. These are actually just simple exercises, but nevertheless we have to see that whatever is being claimed is actually true for once. Let C be a circle in the plane of f, or let's just use this terminology, in f. So let's consider its center and radius. Let u comma v belonging to f Cartesian product f be the center of C, and let W belonging to S be the radius of C. And W be the radius of C, of course, automatically means that W is non-negative. W cannot be negative. By writing the normal inequality here and not the strict one, we are allowing for the possibility that the circle can actually be a point also. That is just this point. Okay. Then the equation of C is, you already know again from coordinate geometry how to write the equation of a circle whose center and radius are given. You just apply the distance formula and the condition that the distance of any point on the circle, from any point on the circle to the center is equal to the radius. So that amounts to writing this: x minus u whole square plus y minus v whole square equal to w square. Again we simplify this, expand all the things and bring it to that form. If we in fact directly write what we are ultimately going to get, it's not that difficult to see how x square plus y square minus 2ux minus 2vy plus u square plus v square minus w square equal to 0. So definitely this equation is in that form where x square plus y square is just that, and a is minus 2u, b is minus 2v, and c is this. So all of them are elements in F. Clearly and minus this belong to F. So that means that's it. Our claim has been proved. Now, if you are wondering why circles and straight lines, that's because those are the objects about which we are talking about their constructibility. That is, whether a straight line is constructible, whether a circle is constructible, whether a point is constructible. So here, instead of talking about constructibility, note one thing very carefully. Now, the moment when we have started discussing about F and plane of F, lines and circles in F, we are not talking about constructibility anymore. We are just simply discussing these things, which so far have nothing to do with constructibility. But when we specialize the case to this, when F will be our field of constructible numbers, then we will see what else we can say. I mean, from these discussions and these considerations, we are going to get something, and to that thing we are going to bring in this situation. In other words, we are going to apply that criterion to this particular subfield, and then something will come out. So we will do that. But right now we are not doing anything that apparently we are doing something other than constructibility. These things on the surface, they so far have no relation to constructibility, but because we ultimately would want a relation, so that's why we are talking about circles and lines. And after these two claims which we have now proved, this line is there in the text. Such circles and lines are called circles and lines in F. Yeah, now it becomes clear why we were writing like that, in F. Okay, so now that we have seen what happens to the equations of these geometric objects, that is lines and circles, when we restrict some things about them inside F, inside the subfield F. Now we can see what happens when you intersect two such objects. What happens to the points of intersection? What about their coordinates? So here are some further things given. Two lines in F which intersect And do you see why we are next considering points of intersection of these objects? That is because that's how, in the original definition of constructibility, we created constructible points. That is, if you take two constructible lines and say they intersect at some point, by our definition, that point is a constructible point. Or say two circles intersect, or a circle and a line intersect. So such points, by our definition of constructible objects, are constructible points. So next it becomes natural to see what happens to those points if our circles and lines are in F. So this is the thing, given two lines in F which intersect in the real plane. their intersection point is actually a point in the plane of F. It seems like that should happen, and this is actually what happens. And this is one exercise. This is exercise 4. Prove that two lines in F, not just any two lines in F, right? So both of them pass through 2 points whose coordinates are in F. That's what all of these things mean. Prove that two lines in F which intersect in the real plane. Is it exactly like that one? The language intersect at a okay. In the plane of F. Now, in solving this exercise and in considering those two lines, definitely we are not going to go back to say 2 points for each line through which they pass, and those points lie in the plane of F. No, we do not need to go that far back. We already know how the equations of such lines look. So we are going to start from there. Let the lines be this is a somewhat informal way of writing this thing. Ideally, I should have written let the equations of those lines be this and this, but you of course understand this language also. Let the lines themselves be this and say plus W equal to 0. Oh, okay. There are some calculations which are a little involved, so I perhaps should not use something other than what I have here. Ux plus Vy plus, okay. Let their point of intersection, because it's given that they intersect in the real plane, so there will be a point of intersection, and there of course will be only one such point. And in general, it's just a point in the plane. Our job is to show that it's actually a point in the plane of F. That means both alpha and beta are elements in F. But if this is the point of intersection, then these coordinates will satisfy both the equations. So we write then A alpha plus B beta plus C is equal to 0, and u alpha plus v beta plus w equal to 0. Okay, now there are some cases, just like in that, I think the third exercise we considered some cases. Here also we are going to consider some cases. So the first thing is this: let b be equal to 0. B may be 0, may not be 0. Let's first see what happens when b is 0. Then a has to be non-zero, because if a is also 0, b is also 0, then c automatically becomes 0, and what is it? This is not a straight line in that case. So if b is 0, then a is not equal to 0, and we have, so what shall we then have from the first equation? This middle term is not there, and a alpha plus c is equal to 0, and a is non-zero. Then we can solve for alpha. Alpha will be equal to minus c divided by a. And because we already know from, is it exercise 3, I think, no? That the equation of that, no, that is the circle one. So from exercise 2, we already know that this a, b, c, u, v, w, they are elements in F. So c and a are both elements in F. So this quotient, in fact its additive inverse, is also again an element in F. That's how we get the conclusion that alpha is an element of F. In this case, when b is 0. Okay, and note that in this case, phi is not equal to 0, as otherwise the two lines will be parallel. Why? Because you see, b equal to 0 means what? B equal to 0 means we get a fixed value of x. Although x is a variable, but on the line we get a fixed value of x, which means what? That the x coordinates of all the points on the line are the same. They have only one value, and that value is minus c divided by a, and which is also alpha. That means what? That means this line is vertical, right? Because only on such a line, the x coordinate of all the points will be the same. The y coordinates will vary. Now, since it is given that these two lines actually intersect, so under this condition itself, if we also have v equal to 0, then this also becomes vertical. So this line is vertical, this line is also vertical. So then in order for them to intersect each other, they have to be the same line. But that's not what we are considering here. For us, these two lines are different, distinct lines, and they intersect at this point. So that's why we are writing, note that in this case v has to be non-zero, as otherwise the two lines are parallel, and how should I write this part? Otherwise the two lines are parallel, and since they intersect, they cannot be distinct. So now V, that's why V has to be non-zero. So now what do we get from this? So non-zeroness of V is going to give us what? Hence, so then what we can do, we can put this value of alpha here. So you will have minus UC divided by A plus V beta plus W equal to 0. And from that equation you can solve for beta. And in doing so, because at one stage you will have to divide by V, so non-zeroness of V is essential there. And the ultimate result is this. What you ultimately get is this. Beta turns out to be UC minus AW divided by AV. Now A is non-zero, V is non-zero, so there is no problem in the denominator, and in the numerator of course there is no problem. And all these things U, C, A, V, W, these are elements in F. So this quotient also is an element in F. Now instead of considering B to be 0, if you consider V to be 0, that is, instead of considering this equation, if you start with this equation and proceed exactly similarly, then also that corresponding alpha and beta will be elements in F. So we write similarly if V is equal to 0, then alpha and beta belong to F. So that means now we can consider that V and B are both non-zero. We can assume that. So we assume that V and B are both non-zero. Right. Since the lines intersect and hence are not parallel, and their distinctness also of course plays a role here. The lines are like this, not like this. So that is why the lines will not have the same slope, because having the same slope is equivalent to being parallel. But now these conditions that V and B are both non-zero allow us to write the slopes of these lines. Just by looking at the equations, you can see that the slope of the first line will be minus A divided by B. Taking this equation in the form y equal to mx plus c, m is slope, c is intercept, that thing. Okay, so the slope of this line will be minus A divided by B, and that of this line will be minus U divided by V, and they won't be equal because these are not parallel. Minus A over B is not equal to minus u over v. And from that we get this condition, i.e. AV is not equal to BU. Hence, and this you have to do for yourself, you have to go to the original equations and solve for alpha. Original equations means this equation and this equation, and solve for alpha and beta in this case, not in those cases, okay? They are gone. Here the only condition is that v and b are non-zero. Whether any other coefficient or any constant term is 0 or not, we are not considering that. It's a general case. So these are the values of alpha and beta. Hence, alpha turns out to be equal to BW minus CV divided by AV minus BU, and beta becomes UC minus AW divided by again AV minus BU. They of course belong to F because the ingredients in this quotients are all coming from F. But note that we do not also have any problem with the denominator due to this condition. AV and BU are distinct real numbers. So that's how we have managed to show that the point of intersection is in fact a point in the plane of F, and this completes the solution. But that is just the intersection of two straight lines. What about the intersection of a line and a circle? Both are in F. That means both are that type of lines and circles. In that case, unfortunately, the points of intersection are not exactly always in the plane of F, but in the plane of an extension of F. And it goes like this. Say you have a line in F and a circle also in F, which just simply means, now that we know from the forms of these equations, that A, B, C, D, E, F, these are all elements in F. And say these two objects intersect. At one point or at 2 points, we don't know, but they intersect. And wherever they intersect, those points are or let me write it like this, that way it will be more clear. Because there may be 2 points of intersection, any point of intersection of the above line and circle is a point in the plane of F. This may happen, actually the point of intersection may be a point in the plane of F, that is maybe an element in F Cartesian product F, or a point in the plane of F root gamma for some positive real number gamma. Oh, I need to write positive here. Gamma in F. So, say it's like this. So you have a straight line like this and a circle like this, both in F, and you have these 2 points of intersection. Then say the coordinates of this point are alpha and beta. Then this alpha comma beta may be a point in the plane of F. That means it may come from this set, or it may come from here. For some positive gamma, which itself is an element of F. So you see that in this case the subfield F is not enough. You may have to consider a quadratic extension of F. Quadratic I say because the degree will be 2. We will see exactly how. So this is the situation, and say you have 2 circles and they intersect either like this, or say they are tangent to each other at a point. But then whatever the situation is, it is again ultimately an intersection between a circle and a line. We will see more about this thing. So this same situation repeats. Once we go through all these things, there are exercise 5 and exercise 6 also, I think, which involve showing these things, these claims, proving these claims. Then we will go to a general result which will tell us something about what happens to the coordinates of this type of points of intersection when you apply such, say, what can I say, such operations, just like compass and straightedge operations. If you apply such operations here in this context, then what type of points do you get? And then link that thing with the field of constructible numbers. That will give us the criteria. So right now we do not have to think too much about what we are going to get, how we are going to get there. Whatever we have seen today, there is no, I don't think there is any confusion about that. This is just something simple. In fact, what we saw in the last video, that is a little complicated, which is about constructible objects and constructible numbers. So I end things here itself. We will continue by showing these other things in the next field theory update. And tomorrow, because we have already gone through Galilean groups and rings once, so tomorrow let's go back to algebra problems from Lee. And with that, I wrap things up for tonight. So see you tomorrow with Lee's problems. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.